So, after today's conversation, I decided to try to give you a little Brecklin live here. So, we're going to do the examples that I missed via video, and we'll see how you enjoy it. So, this first problem involves maximizing revenue from ticket sales. So, we'll just take a quick peek here. We're talking about a hockey team, plays in an arena, has a seating capacity of 15,000 spectators, with a ticket price set at $14. The average attendance at recent games has been 9,500 people, and that's with a ticket price at $14. Market survey indicates that for each dollar the ticket price is lowered, the average attendance increases by 1,000. So if you go down by, say, $2, then the attendance goes up by 2,000. That's 1,000 per dollar. So $2, $2,000, $3, $3,000, so on and so forth. So we're going to attack part A. Find a function that models the revenue in terms of ticket price. Now, this isn't a absolute must, but just to kind of set things up in words and then in algebra. First, the ticket price that we're going to use, right? We're going to use X as a ticket price, and Y is going to be revenue, which is also in dollars. So this is ticket dollars, and this is revenue dollars. So X is whatever the ticket price is, right? So we're going to have varying ticket prices that are connected to varying amounts of dollars brought in from attendance. The amount that the ticket price is lowered is going to be 14 minus X, and Y14 because that's the current price. The increase in attendance is going to be 1,000 for every dollar decrease. So say we have, a $5 decrease, then 14 minus the price of a ticket, right, which would be, say, $9, then 14 minus 9 would give us the $5 decrease. So 5 times the 1,000 would be a 5,000 increase in attendance, right? So this is the piece that tells us how many of the dollar decreases we've had. And attendance is going to be the 9,500 we currently have, plus 1,000 for every dollar decrease. Okay, let's see if we can make sense of that. In more plain language, again, we want to set up a model, right? And the model we want is the function that gives revenue for a given ticket price. So first of all, revenue in dollars is going to be equal to the ticket price times the number of people buying tickets. So that makes sense. The number of tickets you sell times the price per ticket is going to be the revenue that you gain. Okay, so R of X is our function. Revenue is a value that's associated with a number of tickets. So X, again, is the ticket price. And this represents the number of tickets sold. And how is that so? Keep in mind that the number of tickets we're going to sell is going to be the 9,500 that we already do, plus the increase in tickets that we're going to sell for dollar decrease in price. So if we only went down by $2, right? If we only went down by $2, and really I should write that differently, right? So if we went down $2, that's really a $12 ticket. So 14 minus 12 would equal a $2 decrease, times the 1,000 would be 2,000 extra tickets. So the 9,500 plus the 2,000. Okay, so hopefully that helps drill why we have this piece right here. So now what? Now we just crunch down this a little bit, okay? So we're going to have to distribute the 1,000 and combine like terms. So I'm just going to slip in good Brecklin handwriting fashion, the part in between. So when I distribute that 1,000, I'm going to have, the X times 9,500, and then 1,000 times 14 is 14,000. 1,000 times negative X is minus 1,000X. When I combine these two, I get 23,500 minus the 1,000x. Now what? Distribute our x, and we're going to get 23,500x minus 1,000x squared. And what do we have? We have ourselves a quadratic. Now what are we looking for? If we're looking to find the price that maximizes revenue, then I guess as I'm seeing this is a minus 1,000x squared. This opens down. I'm looking for my vertex, that xy set of coordinates is going to be the ticket price that maximizes and the revenue. So that's the price of the ticket, and this is the revenue that we should gain. And again, this is based on some sort of market survey. That's how they got this information. So this is definitely applicable. So how do we answer part B? Right? We're literally just looking for the x value of the vertex. So we're going to use our model, and we're going to stick with just finding the x value of the vertex. Is it the opposite of b over 2a? So seeing that our model was a little bit backwards, keep in mind that b was the 23,500 and a was the negative 1,000. So after we do a little bit of number crunching, 23,500 divided by negative 2,000, and the opposite of all that will be a positive $11.75. So there you go. That's the maximum price of it, or that's the price of a ticket that gives the maximum revenue. Then it says to use the model, we want to know what ticket price is so high that no one attends. So where's no one going to attend? Or where are we going to generate a ticket so high that we have zero revenue? That's going to be the 0 over here. So we're going to set this model equal to 0, right? Revenue of 0 means no one attended. And we end up with the ability to solve this problem. So first thing we're going to do is we're going to divide everybody by 1,000. And by doing that, this is going to give us 23.5. And then this will just be a minus x squared. We'll factor out an x, leaving us 23.5 minus x equals 0. And we'll end up with setting both of these equal to 0. So x equals 0 is here. And 23.5 minus x equals 0 gives us an x of 23.5. So according to this model, a ticket price of $23.50 is just too high. And at that price, no one attends to watch this team play. And it says, of course, if the ticket's price is 0, then you're not selling anything. So no one's going to attend. Or maybe you would max out if you were giving tickets away, really, think about it. But these are the realistic version is just the value over there. Now the question you should be asking is, hey, Don, what if I didn't know to divide everybody by 1,000? Well, you would have ended up with something along the lines of what we have right here. So I can still factor out the x. I get x is equal to 0. And then I get, instead of the 23.5, the big numbers equal to 0. Add 1,000x to both sides. And then eventually I'm going to divide by 1,000. And I'm still going to arrive at 23.50. So either way, you're going to get there. Let's try this again. So what do we have? We have a similar situation. Okay, we have a baseball team that plays in a stadium that holds 55,000 spectators. Current ticket price at $10. The average attendance is about 27,000 tickets. And a market survey indicates that for every dollar ticket price is lowered, average increases is about 1,000. So what do we have? We have to find this function again. So this idea of revenue based off of X dollar ticket sales. So again, X is going to be the ticket price, right? Not the amount that the ticket's lowered, but the ticket price. And so how are we going to get revenue? We're going to take the tickets in terms of price, and we're going to multiply that by the number that's sold. So the number sold is inside this set of brackets. This is the ticket price. And if you multiply the number sold times the ticket price, you're going to get the revenue generated. So how many are we going to sell? Well, we currently sell, the average attendance is 27,000, right? And we're going to increase that by adding what? A certain amount additionally sold. So I had to go behind the scenes and erase my parentheses there. So what's going to happen? we're going to sell an extra 3,000 for every dollar decrease, and the number of dollar decreases is going to be $10 minus the new price. So if the new price is $9, then 10 minus X would be 1 times 3,000. If the new price is $8, then 10 minus 8 is equal to 2. So that's going to be 2 times 3,000, which is going to be 6,000 additional sold, so on and so forth. So here is our new model. Now what? We're just going to do a little bit of algebra. Okay? So revenue generated is equal to X times, open that bracket up, 27,000. Now we're going to do a little bit of distribution. So 3,000 times 10 is going to be 30,000 minus 3,000x. Close that. Okay, now what? We can combine like terms and then distribute x to that. When I combine like terms, I'm going to get 57,000. So that's going to be 57,000x minus 3,000 x squared. And now I have the function in which I would wish to maximize. Now, because this quadratic coefficient is negative, I know that it opens down, and I have a maximum. For the maximum revenue, I need to find a price, and that's my x value. We said x was ticket price. So to find the x value, that's the opposite of b all over 2a. So that's going to be the opposite of 57,000 all over 2 times negative 3,000, which is 9.5, or in reality, $9.50. So it looks like to maximize profit, we really don't need to lower the price very much. We're just going to lower it 50 cents, and that should maximize our situation. But you say, hey, Don, how many people are going to show up? Apparently not many more, because if we're only increasing 3,000 people for every dollar decrease, and assuming that's kind of it's not exactly a linear thing, but let's just assume that 1,500 additional people are going to show up. Well, at $10 a ticket, 27,000 tickets, they're making about $270,000. And according to this model, the max revenue generated is going to be $277.50. And how did I get that? That's the Y value that's associated with an X of 9.5. I put that 9.5 in for X here and for X here, and just evaluated that out, and I got $277.50. And originally at 10 times 27,000, I got 270. So I guess they were pretty close to maxing out to begin with. They're only getting an extra $750. But hey, maybe that's enough to pay you to wrangle out a few hot dogs and bags of popcorn. Our last example is fairly easy. It's fencing a horse corral, and Carol has 2,400 feet of fencing to fence in a rectangular horse corral, and we'll notice that this is going to be X feet wide, and this is going to be 1,200 minus X. And if you think about that, you have 2,400 feet of fencing, and you're building it around a rectangle, then this distance and this distance are the same, and this distance and this distance are the same. So this piece and this piece here should be half of all the fencing. So if you take half of the 2,400 feet, you use X amount of feet over here, you only have 1,200 minus the X amount of feet on this length. It seems to make sense. So if you want to maximize that area, then maximize area of X, right, would be equal to, again, the area of a rectangle is just length times width, or base times height, whatever you want to call it. So X times 1,200 minus X. And when you distribute that, you're going to get 1,200X minus X squared, area of X. If you're looking for the dimensions that make this well-rounded, then we're just maximizing this area. So again, we have a -1 quadratic coefficient. So definitely this parabola is opening down, and the X value will be the thing that we're looking to maximize, right? The Y value will be the actual area amount that is the result of maximizing the area. So let's first find out the dimensions. So what are we going to do? Set this equal to, we're going to find the x value of the vertex, which is opposite of b over 2a, which is going to be 1200. Opposite of that, all over 2 times -1, which is going to be 1200 over 2, which is just 600 feet. So if you put 600 feet right here, 1200 minus 600 is going to be 600. Go figure, if you want to maximize this area, it's a square. Kind of makes sense. So the dimensions are 600 by 600 feet each. And that's going to give us 36 with 1, 2, 3, 4 zeros, or 360,000 square feet is the maximized area. Now, they didn't ask for that. They just asked for the dimension. So there you go. That's your dimension, and that's your function. That was a piece of cake. Just for ha-has, what if we had said, just guessing 700, and this was 500? What would you get? Well, 7 times 5 is 35 with 1, 2, 3, 4 zeros. That's just 350,000. And we said that 600 by 600 was 360,000, right? Square feet. So again, just saying that, a little mathematical know-how would help, and lots of variety of areas. Okay, I don't care what you're majoring in, where you're going. A good number sense is going to put you or poise you to be a little ahead of those around you. All right, that's it. We'll see you next class.